Nevertheless, we're engineers. What's the boiling temperature of water? It depends is the right answer. I was expecting 100 degrees from my mother-in-law. It depends is the right answer. Was I disappointed when she said she didn't know? I have more experience with my mother-in-law than is appropriate to share, so I wasn't surprised. No. Right? I've been married to a daughter for 6 years. I wasn't surprised. Cool. It depends. We'll talk about why it depends, what it depends on. Alrighty. Wow. Cool. Stories. All right. I'm not going to tell any of those stories. So, when we talked about ideal gases, we said, what's an ideal gas? We said there's some assumptions that we use. We say that the particles don't have any interaction with one another except to bounce perfectly elastically off each other, the molecules in the ideal gas. And we said there's no attraction. And we said the volume filled by the atoms or molecules is very small with respect to the overall volume filled by the fluid. Okay? And so we said, well, atmospheric air is an ideal gas. You know, you've got very small particles floating around in a large volume. And we said, well, it breaks down close to saturation temperatures and pressures. So therefore, we'll define pure substances as a substance that's close to or at its saturation temperatures and pressures. Saturation means a change of phase. So we're talking about going from a gas to a liquid in this case. We'd call that, we're talking about that being a point of saturation. When we say, for example, oxygen is an ideal gas, that's true for us in our normal treatment of oxygen, but it's not true if you work at a cryogenic plant. Okay, cryogenics, you're taking oxygen and you're compressing it, possibly to a liquid form. You no longer treat oxygen as an ideal gas. Oxygen is now, for you, a pure substance, because you have to take into consideration the sorts of crazy stuff that happens at low temperatures and high pressures. All right? We consider water a lot, A, because it's very important from an engineering standpoint, and B, because you have some experience with water. So examples of pure substances, water. I'll talk a lot about water today. We'll talk about refrigerants later. But refrigerants, and I've listed 2 of them here, there is a naming guide published by the IIFIIR. It's like the International Institute for naming refrigerants. So they're fun guys you want to invite to your party. But that says what the numbers are. You can reconstruct the what the molecule looks like from the R number. And that document would tell you how to do that. We won't really go into that. We'll just use the refrigerant and the refrigerant data as it stands. So this is liquid. This is water at atmospheric pressure. Okay, so let's do a thought experiment. At 1 atmosphere, and let's take water from something cold, and we know it's liquid. All right. 20 degrees, we're going to add heat in the form of a very powerful candle. And we're going to go from 20 degrees C to 100 degrees C. Okay. And through this transition, all right, the water is rising in temperature and it's slightly increasing its volume. Water gets slightly less dense as you go from 4 degrees C up to 100 degrees C, but it's still water, okay? Then we're going to keep adding heat, and like my kettle on the floor, okay, the water is still at 100 degrees C, but we start to boil off some steam, and this steam is also at 100 degrees C. Okay, so you've got 2 phase. So this would be called the point of saturation. Saturation, okay? This would be called a mixture. This would be called a compressed liquid. Compressed liquid. Or a supercooled liquid. All right? It's in a supercooled state, but we often say compressed liquid because it's not very cold, 20 degrees, so it can be a confusing term. Right? We heat it to the point of saturation. We heat it until it boils, and now it's a mixture of gas, vapor, and liquid. And then we heat it all the way until another point of saturation. And this point of saturation is where it's all vapor. I think they've used the colors wrong. I think this should be gray. But Sengel and Bowles wrote the textbook, so, you know, they probably did some thinking about it. So this is the point where it's all vapor, but it's still at 100 degrees C. So this is the absolute point where if a little bit of heat is removed, some liquid water will fall out of solution. If a little bit of heat is added, you'll go into a superheated state, and indeed we've continued to add heat, and this is called a superheated vapor now. Okay, vapor. The word vapor and gas can be used interchangeably. We often use vapor when we're dealing with pure substances, so that we don't get confused with ideal gases and water in its gaseous state. And so in this case, pressure is 1 atmosphere, it's at 300 degrees C, all of the water exists in the vapor form, and it's not just about to condense out. So if we looked at that on a TV chart, so temperature and specific volume, cooler, good. So where do we start? We started at 20 degrees C. The density of water is around about 1,000. So the reciprocal of density, being specific volume, is around about 1,000th. So my chart just happens to be appropriately, the axis is appropriate. Now, when we increase so we're adding heat, right? So we're going to start at this state point, okay, down here. We're going to add heat, and it's going to slightly expand. So the specific volume is going to slightly increase, the density is going to slightly decrease. Probably not even that much, till it gets to 100 degrees, right? And then it's going to expand, and indeed, so this is logarithmic on the x-axis. It expands all the way up to about 2. It expands a lot, and that's important too. And then, so this is our point of saturation again, okay? Our points of saturation. And then as you add more heat, the temperature rises, so we're no longer constrained to be 100 degrees. The temperature rises, and it also expands, continues to expand, and does something like that. On a logarithmic chart, it's a bit hard to get right. What would happen, so we'll draw that. This is an isobaric process at 100 kPa. What would happen if the temperature wasn't 100 kPa, but was instead 1 megapascal? If you take liquid water at 20 degrees C from 1 atmosphere to 10 atmospheres, yep, right, so we've increased the pressure by tenfold. It compresses, sorry? Does it shift it up? You're getting good. You're getting close. It compresses just a tiny bit, but not very much, all right? It follows a pretty similar line, just a little bit to the left, but a fascinating thing happens when it gets to 100 degrees. And that is nothing at all. Liquid water so we're drawing a 1 megapascal line here. Liquid water at 1 megapascal continues up to about 180 degrees, and then it starts to boil. And it has a boiling line that goes like that, okay? And then, because it's so highly compressed, it's not quite as big when it's all boiled, and then it goes like that, okay? Is anyone surprised by that? Did anyone know that? Yep, good. All right. There's an interesting video. It's too long for me to post. It's like 9 minutes long. But it's guys who boil water at various points as they climb Mount Everest. And you get the opposite effect. So at base camp, water boils at 80 degrees C, right? And that's related to atmospheric pressure as it changes. Now, you could imagine that then at 10 megapascals, let's draw a 10 megapascal line.
All right? At 10 megapascals, you get a very similar point there. It follows a very similar line up here.
Let me refer to my textbook.
I've forgotten. Cool, no worries. And then,
At 310 degrees, nominally,
the water starts to boil. Boil, 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 boil.
all the water's boiled.
Saturated mixture between those 2 points, and then it goes up. And that's your 10 megapascal line, MPa.
Sorry for my writing. Kelman, when he writes on these notepads, is like you could publish what he writes by hand. Me, I'm like, whatever. Draw. So there's a couple of things you might think of when you look at this chart. And one of them is that if you, instead of going in large increments, so here I've done 1 order of magnitude each time, if you went in very small increments, you might get, let's draw it in red. Draw in red, you'd get a point there, right? Well, we know these points. You get a point there, you get a point there. But if you then checked 120 kilopascals, 140 kilopascals, right, you might get a line that kind of goes up like this, okay? And on the boiling side,
You might get a line that kind of goes, I'll draw it as a line, like this. In fact, those lines intersect, and what kind of chart has 374 written on the chart? That's just weird. And in fact, they look like that.
I'm going to cut across to a more professionally drawn version of this, but I wanted you to see how it's developed. We'll talk about why pressure influences the boiling temperature of water as we go on. I'm going to tell it to you like a number of times in a number of different ways in the hope that it becomes intuitive for you. Okay, but this line here would be the line of saturated vapor. This line here would be the line of saturated rated liquid. Okay, because to the left-hand side of that line, it's all liquid. To the right-hand side of that line, it's all vapor. This would be the zone of mixture, where some of the substance is a vapor and some of the substance is a liquid. All right? We'll talk about that point there, and there's a line down here we'll talk about as well. Excellent. Are there any questions, thoughts, concerns, comments? Go.
Why does it shorten?
Why does it shorten?
Yeah,
Yeah, no worries. Yep, I agree. So why does it shorten? So the question is, the length of this line gets shorter as the temperature gets higher, right? Because this is temperature, okay? And the reason is the length of that line is the difference between the density, if you like. It's specific volume, but I'll use density because we're more familiar with it. It's the density of the liquid water when it boils and the density of the vapor when it starts to get superheated. And the reason for that is, if you could imagine lots and lots of pressure, okay, it's pushing the particles closer together, and so therefore, even as a vapor, it has a higher density, okay? And this direction is higher density. Higher density, okay? And so vapor at 10 megapascals, as it approaches all being vapor, is pushed together, and so it's there. The alternative would be at like 5 kilopascals. So I'm talking absolute pressures here, not gauge pressures. So we're talking 95% of the evacuated vacuum, right? You could imagine that water vapor actually is quite rarefied. It's not very dense at all at the point that it becomes vapor. So yes, that line shortens and it has implications for us. The length of that line is a representation of the energy required to boil the substance as well. So that becomes important. Good question. And also? Oh, no. Let lad behind you talk because he rarely talks.
why are you starting at 0.0001 1 over 1,000 is 0.001?
Oh. Because I'm not good with logarithmic charts. What? Did I mention we were going to go to a professionally drawn chart? It's a good question, thank you. And your question was the same thing? No.
What happens above the graph?
Good question. What happens above the graph? Rightio. So at a temperature of about 374, 374.14 from memory, you get to what's called supercritical. This point here is called the critical point, which I will denote CP, critical. Let's talk about atmospheric air. At atmospheric temperature, right, you can't compress atmospheric air enough to make it a liquid at atmospheric temperature, right? So there is a temperature above which, okay, and for water it's 374.15, there's a temperature above which, no matter how dense you make it, okay, so going to the left here for higher density, no matter how dense you make it, those molecules have too much energy to bond as a liquid, okay? So above this temperature is called supercritical, and it's a temperature at which, at no matter what density, you'll never get liquid water condensing out of your substance. So in fact, the compressed liquid region is below that line, and the vapor region is this region inclusive of the space above here. It's a good question. That's the answer. Good, excellent. Are there any other questions, thoughts? I love it. I really like dialogue. Chris?
What happens up to the right of the chart?
To the right of the chart, no worries. So yes, you're right, it's logarithmic. So out here, okay, in this space out here, you need to be really low pressure to get there. So if we did a 5 kilopascal line, I feel like I should do a 10 kilopascal line, because that would be an order of magnitude below our 100 kPa. If you did 10 kilopascals, it would look like that. It would go there, and then it would go like that, and that would be 10 kPa, okay? To start to get into this region here, so you've got really low density at really low temperatures, you need quite an extreme vacuum, right? And I guess there's some, well, is there some sort of limit? No, yeah, so you just get really rarefied air at low temperatures. That's why, so that's low density, low temperature. It's a good question. This is a chart drawn by someone else using a computer. So I would suggest that the everything's a bit better. Oh look, he starts at 0.01. That's just, you know, he knows how to divide by 1,000. So it's the sort of thing that we've talked about, right? I just want to point out a few things, okay? So subcooled or compressed liquid. Subcooled meaning if you add a little bit more heat, it's not just about to boil, and that is the region, okay, off here to the left. So anything there would be called subcooled, right? Saturated liquid, and indeed the saturated liquid line is so labelled here, saturated liquid line, okay, is the line describing when a subcooled liquid becomes saturated. So it's just about, if you add any more heat, it's just about to boil off some vapour, okay? Quality region is in the middle here. We can call that a region of mixture. We can call it the quality region because if you look at the length of this line, okay, so from that point to that point, and you have some point along that line, let's arbitrarily choose a point that obscures 100 kPa. If you divide that number, so this is length, right? Length in millimetres, if you're reading a chart. If you divide this number, let's call it A, by B, x equals A divided by B, right? Then x, and x is the letter that's used, all right? I'm not making this up. X is the letter that's used. We will define x as the quality of the mixture, okay? So if A was almost the same as B, then the number would be about 1. If A was really, really, really short, then the number would be about 0. Okay, so X is bounded by the numbers 0 and 1. We'll talk about quality soon. But where the substance is along that line is quality X, and we use it as an intermediate variable for some of our calculations. Cool. Superheated vapor, right, is this superheat region up there. Sorry, my apologies, that says saturated. Saturated vapor line, superheated vapor, the region over there. We talked about the lines, and we mentioned critical point as well. The critical point is so labelled on this graph up the top. It's the temperature at which any higher temperature can not be compressed into a liquid at all. Excellent. Just a more formalised version of that. I want to tell you stuff a couple of times. If we did something different, if we took water at 100 degrees C, okay, so this is isothermal, and we compressed it from 50 kPa, so it starts as rarefied, so it's all superheated vapor. Notice that the word superheated means it's all vapor. 100 degrees C, you're like, that doesn't sound superheated. No, it's a defined word that means it's all vapor, right? If we lower this piston to such a point that the vapor is now at 101.3 or atmospheric pressure at 100 degrees, so now it's saturated, all right? Okay, question, it came up in the forums. So to have an isothermal process, okay, so it's 100 degrees C, what needs to happen to heat? If we say, that's the first law for closed systems, this is a closed system, all right? What's happened with Q to get from 50 kPa to 1 atmosphere, 101.325 kilopascals? Anyone else? Yes, go.
Would we convert it to the process of phase change from gas to liquid?
We haven't had any phase change. It's a good thought because heat is converted during phase change, but in this case we've gone from vapor to vapor, so there's no phase change. It's a good question. Oh, it's a good thought. Go, Chris. Lost to the surroundings. Okay, so we've done negative work to the system. So this is a negative number, okay? And so Q must also be a negative number. So we've lost heat to the surroundings. Now, it's not an ideal gas, so we can't use Q equals MC P delta T. So we can't use that formula in this case, but it is worth knowing that we're losing heat to the surroundings. Excellent, good. Let's keep compressing the saturated vapor down to a mixture. And you see a mixture involves saturated vapor at the top, saturated liquid at the bottom. They naturally condense out because of gravity, so the vapor is much less dense. And then we get to some point. Notice here the temperature is the same and the pressure is the same. The pressure is the same. And then at some point we compress the liquid to 5 bar. That is very deceptive. That height would not reduce by that much under 5 bar. You wouldn't see the compression at this resolution. But at some point then you get into the compressed liquid state. Okay, so if you did that a number of times at different temperatures now, you would get a PV chart. So the other one was a TV chart. This is a PV chart for water, H2O, and these are lines of constant temperature. So 60 degrees, 100 degrees, feels like 100 degrees should be about 0.1 megapascal, that feels about right. 200 degrees and so forth, and 374 is so marked. At higher temperatures, you can't get water to compress into a liquid, so that's what we said. Saturated liquid line, saturated vapor line, just a different way of representing the same information. It's going. So, man, what we need is like an equation of state, right? Because last week was so simple. PV equals MRT. is there an equation that is just so framed for water, H2O, because we'll use that as a type of all substances? It exists. And I invite you to read that paper. I couldn't get past the preamble. That is by the, it's the International Institute on the Properties of Water and Steam, I think. They invite actuaries to their parties to liven things up. No. That's a joke, right? Anyway, so there is, and it's got about 60 terms in it, right? So it's not PV equals something, all right? It's phi equals the summation from 1 to 30 of, anyway, you can open up, have a look. So for our purposes, we won't use the equation of state. If you're programming this in a computer, you would potentially use that institute's definition of the equation of state. So what do we use in the absence of an equation of state? Well, as engineers, we look up property tables, and it's wonderful, it's great. It's far better than trying to solve it. This is table A6 in your textbook. So I brought my textbook. The publisher gives me a textbook, so I feel like it's, you know, it's hard for me to say, I encourage you to buy a textbook, except to say you're doing 6 months where I teach you how to use a textbook. The resource is potentially valuable afterwards, but that's okay. So this is table A6. You can see, so this is tabulated exactly what we've just seen on the charts. Okay, so I want to try and make that connection with you. Okay, this is temperatures running from 0.01 degrees C and a very low pressure, that is 61 pascals. 61 pascals. So we're talking about 100 kilopascals, right? You're going out of the kilopascal range, down into the pascal range. That's 61 pascals. Through to, and the temperature will go all the way up to 374.15, and a pressure of about 22 megapascals in the table. Cool. So this temperature and pressure define, you know how when we did the compressed liquid example, I said the temperature is staying at 100, the pressure is staying at 101.325, but the volume is changing and we're losing heat. Okay, so this is the temperature pressure couplings. So at 50 degrees and a pressure of 12.35 kilopascals, okay, you get that coupling. And then, you know, at 200 degrees and a pressure of 1.55 megapascals, you get that coupling. So you get this environment where you're going to get a saturated mixture. And so the rest of the chart is then divided into what happens at the extreme liquid end of the line. So there's a line subtended across, right? So the extreme liquid end of the line has some properties. And then what happens at the extreme vapor end of the line, okay? This is a table of properties for saturated water, saturated H2O. So this is just in that quality region underneath the graph, okay? And then there's other tables for the other parts, but let's talk about saturated. So this then defines what happens at the liquid end of the line. Liquid here is denoted F. Doesn't matter, it's how it's done. F, F, F. So this is respectively the specific volume, VF, of liquid water at those temperature and pressure couplings. The U, which stands for, good. I was hoping for like a chorus effect. Specific internal energy, lowercase u, lowercase h, which was a property we introduced Wednesday last week, which is specific enthalpy, and S, which is entropy, which we'll talk about later. Got a question on the forum about it. I'm like, let's not address that. Right, so at the liquid end of the line, this is your density of water. Yeah, as the temperature rises. And you can see, so specific volume, reciprocal of density, they haven't got it wrong. You can see it's about 1 1,000th, okay? And then, let's underline them. G stands for gas or vapor, and this is the properties of saturated water at the extreme vapor end of the line, okay? And so this kind of relates to what we're talking about. The line is longer at the bottom of the chart and shorter at the top of the chart, okay? You can see here that at 0.01 degrees, water goes from 0.001 meters cubed per kilogram to 206 meters cubed per kilogram. That's really far off to, that's really far off to the right-hand side of the graph. At a more reasonable temperature, like 80 degrees, it goes from about the same density to about 3 meters cubed per kilogram. So it becomes more dense, comes in a little bit. So this is describing that curve. The difference between the U values is the energy that you have to put into the liquid to get it to boil at the given temperature, right? So the difference between this value here and this value here is the kilojoules per kilogram of energy you need to put into liquid water to turn it from a saturated liquid at 15 degrees C to a saturated vapor at 15 degrees C, right? So the difference between those, and because we use that difference so often, we've got two properties here, HFG and SFG. This is, if I make it square, that is the difference between those two values. So it's just, they've done the subtraction for you, and we'll find that to be really useful, because otherwise that's a subtraction we do very often. And SFG, difference in entropy, again, so if you wanted to know what 8.01771 minus 0.7036 was, it is 7.3735. Subtraction done. I'm that good. That's a table. We're going to talk about tables a fair bit. I wanted to introduce it. I want you to be comfortable with it. How you doing? I thought I'd tell a story. Has anyone got any questions about anything there? Good. Tables. Table is exactly the same as a chart. We'll use the tables more because they're a bit easier to read than the charts. What's the boiling temperature of water? Right? It depends. You can get water to boil all the way from 0.01 C. You can't get water to boil below that. And we'll talk about that as well. And you can boil water all the way up to 374.14 degrees C. You can't get water boil above that temperature because it's already supercritical. The answer is it depends. Up. Go. Why do we care? Boiling water is a big deal for thermodynamics. We've talked about power stations, steam power stations. We use a lot of it to generate the electricity. That heat that it takes to boil water, we exploit that quite often. And we talked about water, but we can use different refrigerants. We can select a chemical that has a different curve for a given purpose later on. That's that.